Good afternoon. This is Team 6 with our final presentation regarding the problem situation. The team is composed of Luis Cabrera, Luis Guajardo, Ernesto Reyes, Máximo Fajardo, and me, Yael Guerrero. As an introduction, I will give context about the problem situation, which is regarding fossil fuels and some of the different alternatives that we have to solve this problem. In this case, we have different types of renewable energy that will be described in the following slides. So, some of the pros and cons of the problem of fossil fuels is that they have high energy density, lots of energy in small amounts, and it's good for large scale use. Established infrastructure, systems for extraction and transport already exist. Reliability delivers consistent and controllable power. As for the cons, we have environmental pollution. Burning releases CO2 and harmful pollutants. Climate change, a major driver of global warming. Non renewable sources, supplies are limited and unsustainable. And environmental degradation. Extraction harms land, water, and ecosystems. In the following slides, we will present the different types of cells. In this case, we have the solar or photovoltaic cell, the galvanic cell, and the fuel cell. In each one, we will describe which one consists of, what are their pros and cons, and further ado, we will teach the process of how we made the galvanic cell and the results of our experiment. Solar cell. How do they work? A solar cell or photovoltaic cell converts sunlight into electricity using the photovoltaic edict. Sunlight hits the cell, exiting electrons, which start to move and generate direct current. This electricity flows through wires and can be used or stored.
Okay, so solar cells. In the pros, we have that they are renewable energy source. Sunlight is free and sustainable. They have low operating costs because they are cheap to operate after installation. The environmental benefits because they don't have greenhouse gas emissions. The scalability because it works for homes or large scale solar farms. In the cons, we have that they have high initial costs, high upfront costs. They weather dependent because they don't work at night or in heavy clouds. The space requirements because they have large areas and are needed, for large areas. The energy storage costs because storing energy adds to the total cost, right? So, the galvanic cell, how do they work? A galvanic cell has two metal electrodes in separate electrolyte solutions. They are connected by a salt bridge or porous membrane, allowing ion flow but not mixing. So, at the anode, the oxidation releases electrons, and at the cathode, reductions absorb them. Electrons flow from anode to cathode through an external circuit, creating electric current. So galvanic cell, the pros, they have direct energy conversion because they convert chemical energy straight into useful electricity. Portability, they are ideal for small mobile electronic devices, giving them many applications. The variety of chemistries, different combinations of electro materials allow custom voltage and capacity. In the cones, we have that they have finite lifespan because they stop working once reactants run out. In the environmental impact, some use hazardous materials needing a safe disposal. Also, we have the limited energy density. They store less energy relative to their size and weight compared to the other methods.
Okay, so now I'm gonna talk about the fuel of the cell. So you may be wondering how they work. So the fuel cell converts chemical energy into electricity through a reaction between hydrogen and oxygen. Hydrogen enters the anode, where it splits into protons and electrons. So the electric flow of the electrons flow through an external circuit, creating an electric current. Protons pass through the electrolyte to the cathode, where they combine with oxygen and electrons to produce water and heat as byproducts. So now I'm going to talk about the pros and the cons of the fuel cell. Well, one of the pros is that it is high efficiency, so it converts fuel to electricity more efficiently than combustion-based power. It also has a side of environmental benefits with hydrogen emission are just water and heat, so we don't have any of these greenhouse gases that have been affecting us throughout all our life. We also have a quiet operation, so nothing moves around. It means it's silent energy production. So you could have it in your house without making a noise, rather than a combustion power supply. Also, we have the scalability and flexibility. So it has both. It can work on smaller devices as well as bigger devices. What are the cons? High initial cost. So usually talking about fuel cells, even though it's not as new as you would consider it, it is still has an initial high cost as well as a high production cost. Also, the fuel infrastructure challenges. We can see countries like the United States having adapt in a way to these new infrastructures, but it hasn't reached places like Mexico. Talking about general, it hasn't reached a lot of countries. We also have the durability and the longevity. So some fuel cell types, particularly PEMFCs, degrade over time, needing maintenance. This would be one of the cases. We also have the hydrogen storage and safety. Hydrogen, especially in liquid form, is hard to store due to its low energy and density and flammability. In these next slides, we're going to talk about the different steps as well as the different results and how we managed to do all the lab work, so all the practical stuff that we did in the lab.
Objective. So the goal of this project is to design and build a functional galvanic cell capable of generating between 1.5 and 2 volts. To achieve this, we first have to understand and study the key components, like the anode, the cathode, the salt bridge, and the electrolytes. Then, we use redox reactions and standard reduction potentials to guide our material selections based on those calculations. Then, we construct the cell by assembling two half cells and connecting them with a salt bridge and an external circuit. Then we measure the output voltage and compare it to theoretical predictions. And finally, we test the cell by powering a small toy, demonstrating its ability to convert chemical energy into electrical energy in a real-world application. In this slide, we explain how we built our galvanic cell and calculated its expected voltage output. We selected magnesium and copper as our electrodes based on the standard reduction potentials. Magnesium has a very negative potential of minus 2.37 volts, which means it can easily give up electrons. So we used it as an anode, where oxidation occurs. Then copper, on the other hand, has a positive reduction potential of plus 0.34 volts, meaning it accepts electrons more easily. So it acts as a cathode where reduction takes place. The cell potential is calculated by subtracting the anode's value from the cathode's value. So 0.34 minus negative 2.37 gives us 2.71 volts. This means that under standard conditions, our cell should produce around 2.71 volts. On the right, you can see the redox reactions happening in each half cell. At the anode, magnesium is oxidized, so from Mg we go to Mg plus 2 electrons, and at the cathode, ions are reduced. So we have Cu2 plus 2 electrons goes to Cu. And then the overall reaction is Mg plus Cu2 plus, it goes to Mg2 plus Cu. This redox process is what powers the cells and produces electrical energy from chemical energy. This diagram shows the complete setup of our galvanic cell and the function of each part. On the anode side, on the left side, we used a magnesium strip placed on the solution of 1M magnesium nitrate. This is where oxidation happens, meaning magnesium atoms lose electrons. On the cathode side, so on the right side, we used copper strip. We used a copper strip in 1M copper nitrate, where reduction occurs. So copper ions gain electrons to form solid copper. Between the two beakers, so the yellow bridge you can see on the middle, we placed a salt bridge made of filter paper soaked in potassium nitrate, KNO3. This allows ions to flow and maintain electrical neutrality while preventing solutions from mixing. Um, Finally, wires connect the electrodes to a voltmeter or any device we want to power, allowing the electrons to travel from the magnesium to the copper, generating an electric current.
El cuadrado. Dos, cuatro, tres.
Y luego,
Nada más que ocupamos el apoyo de una pila.
El cuadrado. Azul.
no, pues, no, pero si es el apoyo de una pila, ¿verdad, mis? Porque como cada pila es de 1.5.
El círculo. El triángulo. El cuadrado.
Ya. Entonces con este bien se suena. A ver, ingeniero. Ahí está.
Sí, no, sí está pasando. Que no lo- Se está inflando el globo de acá.
Pero es que se llama bien, ¿no? Para que no escape. No, está bien cerrado.
Sí, sí está bien.
A ver, Mac, no le quieres hacer. Así no escapa.
Pues que si no se estaría saliendo el agua en aquel. Si se estuviera escapando. Y se está. Oye,
pero
está apretadita. Sí. ¿Y acabamos?
¿Ya? ¿En serio?
Faltan 2 minutos más.
¿Cuánto tenía que hacer?
Que se infle 2 veces que este. Pero está pasando agua, ¿ya viste? Pues ahí están las burbujitas del agua. No tendré que usar el agua que está en el globito. No.
To meet our goal of producing 1.5 to 2 volts, we built a galvanic cell using magnesium as the anode and copper as the cathode. The cell used magnesium sulfate and copper sulfate solutions as electrolytes and a potassium nitrate soak filter paper to maintain charge neutrality between the half cells. Once assembled, the cell produced a voltage close to the theoretical 2.71 volts, enough to power a small toy. This confirmed the strong redox potential of the magnesium copper pair. However, due to the high reactivity of magnesium, led to faster degradation over time compared to other metal combinations. We found that electrolyte concentration, electrode condition, and salt bridge placement had a major impact on performance. Issues like partial immersion or contaminated solutions caused voltage instability. Consistent results were achieved by using clean electrodes, fresh solutions, and ensuring tight connections. Using freshly prepared solutions and ensuring tight clean electrical contacts consistently improved the reliability and output of the cell. So, after showing our lab work and discussing the results, we will talk about our conclusions. Through this project, we gained hands on experience in electrochemistry by building a working galvanic cell. We learned how redox reactions drive the flow of electrons, how to calculate standard cell potentials, and how to apply this knowledge to design a practical energy source. Testing our cell with a toy was a valuable part of the experiment as it provided a clear and tangible demonstration of our cell's functionality. It reinforced the connection between theoretical chemistry and real world applications. This project highlighted both the potential and limitations of simple electrochemical cells and gave us insight into how batteries work at a fundamental level. So, after performing the experiment, we have several recommendations. For example, improve Salbridge design, use fresh electrolyte solutions, standardize electrode surface, use a multimeter to monitor voltage, scale up for greater power, explore alternative metal pairs, and finally, seal the system to prevent evaporation and contamination.